It's late at night. It's late even for me, and but I wanted to get this video up. This is Test 3 review, and we will start with the multiple choice questions. I'm going to try to zip through this quickly. We can go through it in more detail in class. Okay, number 1. Circuit A is a resistor R ohms and a capacitor of C farads connected in series with a switch. When the switch is closed, it takes 80 seconds for the capacitor to discharge. So this is what we have. We have this thing here, 80 seconds for the capacitor to discharge to 37% of its initial charge. If another capacitor of C farads were added in series with the first, how long would it take for them to discharge of 30 to 37% of their initial charge? Okay, so we're just going to call this C0 and R0. Those are our starting values. And we know, let's see, first of all, we know that the charge goes as Q of T equals Q0 e to the minus t over RC. So when does Q of T equal 37% of Q0? That would be when e to the minus t over RC equals 37%, or 0.37, which would be when e to the minus t over RC equals 1 over e, which means that RC, if minus t over RC is 1, then RC is going to equal t. I'll just leave it at t for now, but we're given that t is 80 seconds. All right, so now I'm going to fix this and complete it. R0, C0, our starting values, R0, C0, they equal 80 seconds. Okay, so when does if another capacitor of C farads were added in series with the first, how long would it take them to discharge 37%? Well, we know R0, C0 is equal to 80 seconds. So what happens if we replace C0, if we add another one there? Well, when we add another capacitance in series, it's 1 over C plus 1 over C, and the inverse of that. Well, what is that? That's C0 over 2. You should know this now from identical ones, but you can also just add it and figure it out. C0 over 2. So our new value for RC is now R0, C0 over 2. So the question is, what t does this equal? What is this t? Well, if R0, C0 is 80 seconds, then this would be 80 seconds over 2, so 40 seconds. The answer is B. All right, next thing, for the same problem, as a matter of fact, I'm going to go ahead and leave everything up here. For the same problem, another resistor of R ohms is added in series. So now we have another R0 here. So we have an R0 there. So now we've gone from this. We're now going to add another R0. Well, how do resistors in series add? It's just R0 plus R0. So our new resistance is 2R0. So now what we have is our new R times C is 2R0 times C0 over 2, which just equals R0, C0. But we already know R0, C0 is equal to 80 seconds. So the answer here is A, 80 seconds. Okay, isolated parallel plate capacitor holds a charge Q. Distance between the plates is doubled. What happens to the electric field? All right, so for this one, we're just going to go with a couple definitions that come straight from the equation sheet. Okay. That comes straight from the equation sheet. We're just going to start with capacitance, for example. C, let's do it this way. Yeah, okay, I'm sorry, I should have left that. Well, I'll do it because I'm going to do this in 2 steps. Okay. C is defined as, you will remember, Q over V. Well, what does that mean? It means that Q is equal to CV. All right, so that's fine. What other definition do we want? Well, let's use this. V for a constant electric field, which you guys know that's what you have present in a capacitor, is equal to, well, I'm sorry, I should have said E for a constant electric field is equal to just delta V over delta X, which in this particular case, what does it happen to be for a capacitor? That's just V over D, right? It's just from here to here. We have a certain voltage difference, a certain distance, and so the electric field is just defined. And once again, straight off the equation sheet. So let's just put these two things together. We have Q equals CV, which equals C, and I'm going to multiply both sides of this by D, so which equals C E times D. Well, what's the only other thing we're told? We're told it's a parallel plate capacitor. Also, right from the equation sheet, parallel plate capacitor, C equals epsilon 0 A over D. So we're just going to go ahead and put that in here. Epsilon 0 A over D times E D equals Q, the charge. Well, the D's cancel. So we have epsilon 0 A E equals Q. Now, this is an isolated capacitor. What happens for an isolated capacitor? An isolated capacitor means it's got a Q and there's no place for the Q to go. So Q does not change, which means therefore E does not change. E remains the same. You can also just go back to remembering Gauss's law. When we did the Gauss's law problem for parallel plate, what was the electric field of that parallel plate? Did it have a distance involved in it at all? No, it did not. It had, or even when we were talking about an infinite sheet, just sigma over epsilon 0, I think that's right. But in any case, has no D involved in it. And so that's what a parallel plate capacitor essentially is. So you can just go back to that. Oh, and the next problem is, I shouldn't have erased everything there, but that's all right. Next problem is what happens to the potential difference between the plates in the previous problem. So we now know we've gone from, we have Q, we now went from D0 to 2D0. All right, and once again, what do we know? We know the capacitance. Actually, what's the easiest way to do this? Yeah, let's do it like this. C equals Q over V, and what happens to the capacitance? It was epsilon 0 A over 2D0. That's what we now have. Has Q changed? No, because it's an isolated capacitor. So this equals Q over V. So now we just want to compare our first Q. We'll just do it like this. We'll want to compare our first V to our final V. So I'm going to just mess with this a little bit and just say V equals 2D0Q over epsilon 0A. Well, what was it to begin with? Well, this D, instead of being 2D0, was just D0. So what has happened to the potential difference? It has doubled. Okay, so that was B. All right. Circuit has a resistor R1, battery, and other components. Another resistor is added in series. Which of the following occur? The power dissipated is reduced. The voltage drop is reduced. Both A and B, not enough information to say. Okay, so what do we know? We went from R1 and we added another resistor in series. So we went from R1 to R1 plus delta R. We have no idea how much this is, but we know it's something. So what do we know about the voltage drop in this what do we know about the current in this circuit? We know we had some certain resistance and we added a delta R. So if I equals V over R and it now equals V over R plus delta R, then what has happened to I? The I has dropped, so the current has gone down. If the current has gone down, what is the dissipated power? I squared R. So if I goes down, and we're just asking about the dissipated power for R1, So if I goes down, what happens to this? It goes down. What's the voltage drop across R1? It's just IR1. And once again, all this stuff is on the equation sheet. So IR1, is this bigger or smaller if I goes down? R1 stays the same, I goes down, this has to go down. Therefore, both A and B must be true. Now, circuit has a resistor R1, a battery, and other components. Another resistor is added in parallel. Which of the following occur? The power dissipated by R1 is reduced. The current through R1 is reduced. Both A and B, not enough information to say. So I am actually going to, I gave everybody 4 points for this question because I realized I did not really ask what I want to ask, because really the true answer is none of the above happen when you have a resistor added in parallel. So I'll leave it at that, and you guys can figure it out just by doing that equation in parallel. All right, number 7. 3-volt batteries connected to a series circuit containing 2.5 volt and 12.5. Okay, I'm sorry, 2.5 ohm and 12.5 ohm resistors. So I've got this and this. Oops, let's do that. Okay, this is our, I'll just label V, R1, R2. But we know V equals 3 volts, R1 equals 2.5 ohms, R2 equals 12.5 ohms. So what's the total resistance here? The total resistance, these are in series, so total resistance is 15 ohms. So if I want to know what I is, that's V over R, that's 3 over 15. That is 1 over 5, that is 0.2. So now if I want to know, what am I asked? What is the voltage compared to the negative terminal, this position here, of the point between the two resistors? Okay, and so at this point, I want to know this voltage. If I put a voltmeter right in here, what's the voltage right here? Well, what does that mean? From here to here, it's going to be plus 3. And then what is it here? You're going to minus IR1. Well, what is the I? I is 0.2. So just 0.2 times 2.5 is going to be 0.5 volts. We start from 3 minus 0.5. The voltage between here is 2.5 volts. There is one possible confusion in this question in the way it was stated, but only one person pointed that out to me. I did give that person some partial credit, and maybe I can't remember what I gave him. I gave him at least partial credit. So, all right. But for everyone else, this was clear enough. Okay. Same number 8. 3-volt battery connected to a series circuit containing a 12.5 ohm resistor. That's this one here, R2. It has an internal resistance of 2.5 ohms. What is the terminal voltage compared to the negative terminal of the battery? Oops, yeah, of the battery. Okay. Is there anything different about this circuit? The only thing different is that we are looking at this point and this point as being the two terminals of the battery now. This is now the internal resistance of this battery. Has anything else changed? No, nothing at all has changed. Therefore, 2.5 volts is the answer. All right, number 9, look at the following circuit diagram. How's the current at point A compared to the current at point B? All right, some of you made an assumption that was an incorrect assumption. And I think only a couple people made that assumption. But here's the drawing. The drawing is this, that, this, this, this. All right. So what do we have here? Well, if we were going to do Kirchhoff's loop kind of thing, we could do this. We could have an I1, I2, I3. and we would know I1 plus I2 equals I3, and we could also do other things, right, with the voltages, the voltage A, voltage B, whatever, etc. Okay, so we're asked, between points A and B, how does the current compare at those 2 points? Well, what do we know about the amount of I1 or the amount of I2? We know nothing. What do we know about this R1 and R2? The assumption that some people made was that these were all the same R. I did not say that. I did not say that intentionally, because the whole idea is I want you to look at the circuit and say, what can you say about it even when you don't know any of these things? And the answer is, for this, you can't say anything about what the current here is compared to the current there. So, not enough information to say is the answer. However, now let's do the same exact drawing, except we're going to shift point A to right here. Now that we shift point A to right here, look at this point, between this point and this point right here, between these 2 points like that, what is that circuit? It's only a series circuit, one loop. The current inside one loop of a series circuit must be the same. That stream in the woods analogy, if you want anything else, there's no place else for that water to go until you get to these junction points. So point A and point B must be exactly the same. Okay, that's it for the multiple choice. We can go over more of these, we can go over these more in class if you would like, but that's all there is to it. Okay.